Good evening, Professor, once again. We start the session. So, I request my student to introduce the guest. Asubas, can you say introduce?
Good evening, sir. Dr. Franco Fernando Yanin is a professional engineer, researcher, and academic at the Faculty of Engineering of Universidad Finis Terrae in Santiago, Chile, and professor of the MBA of Universidad Técnica Federico Santa Maria, also of Chile. He is also an industry consultant for several companies. Dr. Fernando received his MSc and SCD in Industrial and System Engineering from Pontificia Universidad Católica de Chile in 2014. Sir also holds BSc in Electrical Engineering from the University of Texas at El Paso, USA, a Bachelor of Science and a professional Civil Industrial Engineering title from Universidad Arturo Prat at Chile, and MSc in Industrial Engineering from the University of Santiago de Chile. His research interests and projects include technological entrepreneurship, engineering sustainability, and sustainable hybrid energy systems for on-grid distributed generations, where Sir works closely with ENEL in Chile, thanks to grants and scholarship awarded by the Chile government. His performance, enterprise systems, industrial organization, and management. Dr. Yanin is an active researcher and member of several research network and advisory member of local organization dedicated to sustainable energy and environmental. Thank you, sir.
Thank you very much. Thanks for the presentation. Before I begin, I'd like to thank very especially my friend, Professor Dr. Sarat Kumar Sahu, with whom I have a very long friendship, very wonderful friendship of many years now. And I'm very honored and pleased, it's a pleasure to be here with you all and to share my research. Well, let us begin providing some context.
Professor,
Essentially,
Professor,
yes.
Please put your PPT slide mode, full screen slide mode. Slide show mode.
What was that? Sorry.
Presentazione con diapositive.
This full screen. Yeah, it's fine. It's fine.
Okay. So today's power generation and distribution industry is facing several challenges. For example, in Chile alone, the country where I live, you have problems with earthquakes, quakes, several quakes throughout the year. Some are very, very strong quakes. There's also problems with violent weather. We've had, for example, in 2024, several issues with strong winds and rain, and that made several parts of Chile, not only Santiago, but several other areas of Chile without electricity. It affected the power lines. It brought down big electrical posts and stuff like that. So it was terrible. So the electrical utilities in general, and in particular this one that I'm working with, I've been working them for several years now. I've been collaborating with Enel Chile. Enel is one of the largest utilities, electric utilities in the world. It's Italian, and they have the largest distribution of electricity here in Chile. Okay. And they've been preparing for this. They're taking action. Okay, they're taking several measures. Among them is considering distributed generation systems, okay, to, taking advantage of the large presence of photovoltaic systems here in Chile. So the question is, how do you reconcile the electric power from the distribution grid, right, with these these distributed generation systems that are essentially small and medium-sized photovoltaic plants, okay? Why photovoltaic plants? Solar photovoltaic is very economical now, is very cost effective in Chile. And we have wonderful sun, we have solar radiation that is one of the best in the world. We don't have very much wind in the central part of Chile. We have some good wind in the north, way back north, and some parts of the south, okay? So homeostaticity of energy systems is a way to reconcile, power and energy management coming from the grid and from distributed generation systems like small and medium-sized microgrids, okay? The homeostaticity of energy systems seeks to bring about rapid, effective, and efficient equilibrium between supply and demand, okay? There are also several normative issues with the law that are coming up, and that have come up during last year. For example, complex changes in the law that have obliged electrical utilities to accommodate the growing market of distributed generation systems. You have, for example, Law 21,667 of April 2024, which is a law that unfreeze electric tariffs. Electric tariffs, because of the pandemic in 2020, were frozen. Okay, we have a freeze. We had a freeze of electric tariffs, and people just forgot about it. Many people were out of work, and so to avoid an economic burden on the population, they froze electric tariffs. Well, that was ended last year, and it was a big jump in electric tariffs. Okay, so the cost of electricity went up significantly. I'm talking about 40 to 60% in some cases. That pushed again more people to consider installing distributed generation systems, for example, in buildings and in the homes. Okay, we have now in Chile about 13,000 to 14,000 homes in general, overall, that have solar panels installed, and that way they can get electricity from photovoltaic generation. But that's growing, okay? And that's one of the issues. The cost of electricity has gone up significantly. And the other thing that I said is that you need to accommodate the electric power systems, the utilities, the electric utilities have to accommodate this growing landscape of distributed generation in different parts of Chile, okay? And this is also happening in Peru, in Argentina, in Latin America in general, because of the cost of electricity. So there are several challenges, in some of these are, especially with the laws, the laws are coming to integrate more and more distributed generation, and that is also affecting the utilities, because the utilities are used to providing electric power, on a central basis, and now they're having to accommodate all these distributed generation systems, these small and medium-sized microgrids that are being connected to the grid, So how do we enhance control and energy management systems in distributed generation systems? That's the big question, okay? And that's where my research on energy homeostasis, and in particular, this energy homeostaticity concept that I introduced, and that I've been working with Enel in collaboration with them, comes up. The theoretical groundwork underlying the subject, as well as other relevant contextual factors, are also discussed here in this presentation. And in that sense, the research has found that energy storage is very important. Why is this? Because it enhances homeostasis model. It provides also a way to have disposable energy, available energy in times when there's no sunlight. Okay, and so people now that energy storage has come down in cost, it's come down in price. uh, Communities are realizing that is more cost effective to buy batteries, set of batteries, and to have energy storage on, besides having, photovoltaic generation going on through the sunlight hours. Okay, because if you don't have any way to store energy, you just have to depend on the grid. Okay, the time you don't have renewable power from the solar photovoltaic generation, you have to rely on the grid, and the grid becomes very expensive, especially during the fall
Hello.
and winter months. Okay, after 6 p.m., the cost of electricity goes up. The ability to control and optimize energy and
Hello, sir.
power
Excuse me.
consumption. Yes.
Can you repeat this word again?
Which which
Yes,
word do
yes.
you want me to repeat?
Yeah, please
The
tell me
ability
what
to
is the problem?
control. Excuse me.
No. What we are discussing now, can you repeat once again, please?
No. Oh, that means we didn't get you.
Sir,
I'm
discussing
talking
this
about
word.
how you excuse me. I'm talking about how you reconcile energy management and power management when you have grid supply and distributed generation systems working at the same time. That's what energy homeostasis and energy homeostaticity is all about. Okay, the ability to control and optimize energy and power consumption at the end user level by means of demand response, for example, is something that electrical utilities are exploring very, very heavily now, because they have realized that they can group customers. The different customers have different electrical habits. Okay, some are more intensive in power consumption, others are just much less power intensive consumption. Okay, so another thing that is important is many buildings in Chile are establishing or imposing some thermal and electrical constraints to limit the system's power consumption when green energy is present. Why is this? Because they want to maximize renewable power so that there's less dependence on the grid, okay, less reliance on the grid supply. Why is that? Because of the cost. Okay, we have big malls, for example, and hospitals and places like that. There are ways where you can impose or create thermal and electrical constraints so that no, not you know, you can limit the system's power consumption in ways that doesn't affect the overall operation of the building, for example, and that helps save energy and also cost, brings costs down. So energy efficiency is very important in that sense. There are many proposals also to scale energy, distributed energy in systems, it's photovoltaic, like I said before, because of the cost. The cost of photovoltaic energy in Chile has gone down significantly. It's much cheaper than it used to be, So it's very, very convenient nowadays. And electric utilities are seeing that this is, a market that is growing and that they have to accommodate, because all these microgrids are connected to the grid. Okay, they don't work independently. They're all connected to the grid. They can work on island mode if there's need for that. For example, if the grid goes down, you can have your microgrid, working. And because of the weather issues that I mentioned before that are affecting Chile, and these quakes and stuff like that, there's also some arson and people that are setting fires. All that is creating problems, and we need to secure electrical power consumption and distribution. So the distributed generation systems is an option that is growing. There's another law that has some time now, so several years now in Chile, which is 20,571. This law, which is in place, and many people have taken advantage of this law and continue to do so, grants people in Chile the right to generate their own energy, okay? Self-consume it and inject the surplus into the grid. So if you have a significant amount of energy generation, electrical energy generation, with a small photovoltaic plant, you can inject what you don't consume. You can inject it into the grid, and you will sell that to the electrical company and be paid a contract tariff, a price that is less than what the big power generation companies sell, to the distribution company, because the big power generation companies that are way back in the north and some in the south, they have to pay. Also, they have the cost of transmission, which you don't have. This is small and medium-sized generation, through photovoltaic, don't pay any transmission. They don't have any transmission. They're right there, and they inject their surplus to the grid. So there's a regulated tariff, a price that you get, that they pay you for that surplus of electrical energy that you inject into the grid, and they are obliged, they're forced to take it. Microgrids are built for a purpose, okay? And the purpose today in Chile is essentially to, for one thing, bring down the price, the cost of electricity. And in the other is the fact that when you need to secure electric powered supply, and a way to secure it is essentially to have this alternative generation through photovoltaic plants. The decision to use batteries or not to use batteries becomes essentially on the community. Okay, like I said before, people are considering more and more now to have energy storage. And why is that? Because energy storage has come down in price. It's still not cheap. It's not cheap, but it's more affordable than it used to be. Okay. And sometimes when you realize that because of the price of electricity that has gone up significantly, you realize that you can save money, on the midterm by buying this energy storage and storing energy and having that energy after 6 p.m., for example. That really makes a difference. Okay, so you also have these communities, for example, people in homes that are dependent on electricity 24 hours a day. For example, people with kidney dialysis or dialysis, and other people that are connected to machines because they have medical problems. All those, you need to have electricity always at all times. And like I said before, because of climate change, and because of these violent weather phenomena that we get sometimes, the grid goes down. Okay, like for example, in Santiago, which is a very large city, if you have a strong wind, you will have power lines go down right away, and you will have several large sectors of the city without power, blackouts, like I call. And so, facing that challenge, like we did in 2024 last year, you need to have these energy storage, and electric utilities are very, very well aware of that. Okay, so and like I said before, they're also working on consumer groupings, energy consumer groupings in residential buildings. They're identifying different groupings, different profiles of consumers, and they're trying to accommodate, based on these profiles. Okay, why is that? Because they want to essentially distinguish between different energy consumption groups. Okay, which you do have. You have, for example, office buildings which have a very, very distinct energy consumption profile. And then you have a variety of residential buildings. They have different energy consumption profiles. So you can work, your supply in terms of that. You can customize. And that is also something very new, something that we didn't have before. Okay. So again, like I said before, many buildings nowadays are installing electrical and distributed generation systems, to provide electrical energy supply based on photovoltaic systems. Okay. And I already said, because of the cost effectiveness of photovoltaic, solar photovoltaic in Chile. But there's another issue which was also brought up by the law, the changes in the law. In Chile, for example, today, and this is a law that was passed some years ago, all right? So it's everybody knows about it. And the construction companies, the immobiliaries, all the developers are aware. Santiago, for example, and other big cities in Chile, same thing but in other places. They're full of buildings. Okay, buildings are coming up everywhere. You have, for example, big cities where the scenario is more and more concentration in certain sectors of the city. So there's also more density. Okay, so you need to really worry about the electrical energy demand, in those sectors, especially because of the concentration, the density of population. So in Chile, it's mandatory by law that all existing large public and commercial buildings, I repeat, mandatory by law that all existing large public and commercial buildings more than 250 square meters, that or bigger, must incorporate photovoltaic energy from 2027 onward. So in 2 more years, they'll be obliged, okay, to incorporate photovoltaic energy from that year on. Starting in 2028, all new government and commercial buildings, regardless of size, must also incorporate solar energy, photovoltaic. So there you have it. The government is pushing this everywhere. So utilities have to realize this, and they have to accommodate this. Okay, because they're all connected to the grid. Okay, so they can provide stability and also be a backup system, in case the system goes down. And that's where the concept of homeostasis is so important, because you emulate essentially living organisms in homeostasis. Homeostasis is present in every living organism, okay? And what we do here is we emulate this concept with this property in electrical energy systems, okay, in energy generation system, where you manage energy and power consumption and distinguish between the two. This was first introduced back in 1979 by a famous engineer from MIT, a professor named Fred Schwab, okay, who's now deceased. He and his group, back in 1979 and early 80s, introduced this concept. Okay, now what he advocated for was to have a market, where you would pay for electricity based on your power versus energy consumption. Okay, so he advocated to distinguish, those users, those consumers who were more power intensive, for example, in commercial and in other communities where they use much more power, and other places like, for example, in office buildings, or in some residential, middle road people, regular people that are in very much energy consumers. They don't have big peaks of energy. So that way you can accommodate your supply and maintain a more stable power supply, okay, especially in places where you have much concentration, much density of population, like, for example, in Santiago, Chile. So I already mentioned, and you guys know about energy homeostasis, of course. You probably read my papers. But the biological principle is very clear, okay? So the objective is to keep all of the conditions of the system, stable, okay? You keep enough energy in the batteries, for example, you apply load monitoring and you avoid excessive consumption in order to keep the system stable and continuous. For this, it's very important to keep continuous feedback between the energy supply, generation, and consumption. Okay, that is also advocated. What was also advocated by Fred Schwab and his group. And today that's extremely possible. That's very, very possible because we have the technology. We have Internet of Things. We have wonderful communication systems. So we can keep continuous feedback between energy supply, generation, and consumption. And the consumers can see what they're consuming and from where they're consuming. They can be aware, they can realize how much power, renewable power is being generated and how much they're consuming and how much power is in the system, for example, in energy storage, etc. Let's talk about a bit about the exergy content, the role of exergy here. If you have a more efficient system, a system that can use better energy, and produce more energy, okay, you have a higher exergy content, okay, and that's what we also look for here. Exergy, as you all know, is a thermodynamic concept that can be defined as the maximum useful energy or useful work extracted from a system as it reversibly comes into equilibrium with its environment. Likewise, exergy is also a measure of energy quality and is defined relative to the system's environment. Whenever the energy efficiency of the electric power system is raised and there's more energy available in the system, to supply electricity to consumers, the exergy content is higher. And that is the goal here, to have a higher exergy content. This is also a concept that I developed, the sustainable block. What do I call the sustainable block? Well, if you have a community of consumers, you have the grid, the power, the electric power grid, and you have a microgrid, okay, a photovoltaic plant, for example, with energy storage. That's what I term a sustainable block, okay? And you can make a sustainable block more sustainable if you keep more energy in the system, especially renewable energy, okay? As a whole, the higher the level of autonomy and efficiency of the community, the better they use the energy being produced by the photovoltaic plant, for example, and the way they're able to consume energy more thrifty, and more efficiently, they raise the level of exergy. Okay, so that's important. One of the advantages of this type of control also is the scalability. Okay, you can scale it up and down. I talked already about thermal and electrical constraints, so I won't go into that anymore. It's being done, So in the context and scope of energy homeostaticity for electrical and thermal energy management and intelligent control, we had a very important paper published on that, allowing much needed electrical utility customer integration and coordination described, both of which cooperate in search of optimal use of electrical and thermal energy. What I mean by this is that energy homeostaticity of energy system also cooperates towards a more efficient thermal and electrical energy management. Okay, and many buildings today, I mean, most buildings today, I would say, are trying to manage thermal and electrical energy in a way that optimizes the use of energy, okay, that is more efficient. And that's long known for years, in other parts of the world. There you have one of these large buildings, this was done in 2016. This is a public building, a big public building. They install solar panels. There you have a home in a part of Santiago. And these homes like this, you see them everywhere. Again, Santiago is a city that has certain sections that have homes, but largely more and more are turning in buildings. Okay, buildings are turning up everywhere, and so densification of the city is increasing. Okay, and for that reason, we need to think of these ways to provide alternative energy. And that's why I show you the law, the mandatory law that by 2027, every building will have to have a photovoltaic energy plant installed on it, okay? It doesn't say anything about energy storage, because why? Because you have the grid, always as backup. But again, like I said, the cost of electricity in Chile, for example, has gone up significantly. I mean, I'm talking about over 60% in some cases. So people are realizing that they're better off installing energy storage and having, some energy storage device, usually batteries of some size, that they can store enough energy and have that at their disposal, instead of just relying on the grid, because the grid also comes down, sometimes because of weather or quakes. So that's an issue also. The context of energy sustainability and energy system resilience. What I have termed energy homeostaticity is essentially a new concept. It's not that new because I've already published several papers on it, okay, but it's a concept that I'm still investigating, I'm still doing research on it to try to incorporate this on microgrids, okay, on photovoltaic plants of different size, okay. It's defined as a property of sustainable energy systems to adjust themselves. What I mean by adjusting themselves, well, they are able to act rapidly and bring about change and provide a stable equilibrium between supply and demand. Basically, the energy system has the ability to respond to challenges and perturbations, whether it's from the weather or, problems with the sunlight or, for example, a glitch in the system. They can act rapidly and effectively in fractions of a second so as to restore the system's operation and stability and continuity. So that's essentially what energy homeostaticity is all about. Okay, the ability to recover itself. Okay, to effectively recover itself and to become stable again and continue providing supplying power. The essential point is not only to preserve system stability and continuity of operations in electric power systems, but to reach and maintain optimal equilibrium of the energy systems. The equilibrium thing, is the key point. And for that, you have two concepts: reactive homeostasis, which means you react based on a stimuli to, for example, be a feedback enable mechanism. You react just like the way you do it in living organisms. Okay. The proposed application of energy homeostaticity for microgrid integrated to the grid and operating and building rooftops is one of the papers. And there's a figure that I'll show you now. This one, okay, where you have a sustainable hybrid energy system. That's what I call a sheet. Essentially a photovoltaic plant of some size. A small or medium-sized microgrid. Then you have the power supply, you have the sustainable loads, energy consumption of some kind. You have the homeostatic control in the center, you have power supply being adjusted based on the block's homeostatic responses. We'll see about the equations a bit later. And there you have the grid connected sustainable hybrid energy system, always it has to be grid connected. And you have the power supply. So this is essentially the model in being represented here in this simple diagram. Now, the concept of energy homeostaticity and reactive and predictive homeostasis, which are part of the energy homeostaticity model, are very they're very linked, they're very connected with the concept of grid flexibility. What we call grid flexibility, we call it the grid's capacity to adapt to fluctuations in energy demand and supply. That's as simple as that. Capacity to adapt to fluctuations in energy demand and supply. For example, the introduction of capacity-based tariffs in Belgium some years back resulted in 8.3% improvement in grid efficiency. Okay, that was in the news. So energy homeostasis relies on reactive homeostasis control and predictive homeostatic control. Okay, reactive response after deviation occurs. Predictive anticipates changes and adjusts in advance the system. Okay. And that is today possible because we have wonderful means of data analysis. We have weather control, weather forecasts. We have all kinds of technologies that can allow us to have good predictive control. Okay. So the methods of engineering electric grid flexibility, as we see it in our research, is demand response programs, energy storage solutions, and involves technologies such as predictive control mechanisms and strategies that allow the grid to dynamically adapt to changes in energy supply and demand, improving efficiency and resilience. That's the big thing, okay? Distributed generation offers efficiency, flexibility, and economy. Those are the key issues, the key benefits of distributed generation. And is thus regarded as an integral part of sustainable energy future. That's true in Chile and in the countries in the South region, okay? They're all following the same model as Chile. Grid flexibility in that sense is essential for integrating renewable energy. Like I said, in Chile is largely photovoltaic energy and maintaining grid stability. Improved load balancing, for one thing, using predictive homeostatic control and reductions in grid disturbances. Okay, there's a famous paper that was published in 2019 called Design Simulation of Energy Homeostaticity Systems for Electrical and Thermal Power Management in Building with Smart Microgrid. That was published in Energy's journal, and it was very celebrated. The main focus of that paper was integration of electrical and thermal systems. Like I said before, today it's very important to integrate both and to manage both in a way that can be more efficient for residential buildings, okay, and for also for the commercial buildings as well. The outcomes for that is we demonstrated energy savings through synchronized homeostatic control. So basically what you get is energy savings, and with that you bring costs down through homeostatic control. The main advantages is integrating thermal systems with electrical loads improves efficiency, okay? And that is nothing new. An electrical engineer, we know this for many years now, So there are several examples of energy optimization doing this, especially in what is called smart homes, okay? Which are, I don't know in India if there are many but in Chile, for example, there are some neighborhoods that have smart homes, because of the technology has come down in price, so they're using that more and more. There are two papers here that talk about this thing that I just mentioned, that I just showed you. Design and simulation of energy homeostaticity systems for electrical and thermal power management in a building with smart microgrid, which is the one I just mentioned. That was published on 2019. And the other one is grid-tied distributed generation systems to sustain the smart grid transformation, tariff analysis, and generation sharing. This tariff analysis is essentially how you provide, different tariffs for those people. You group consumers like Fred Schwab used to advocate, and you distinguish people that use less energy, that are more thrifty, and that can benefit more from renewable energy. And these people pay a lower tariff, so that people that are more intensive power consumption can have more at their disposal. That is treated in this paper and is very interesting. There's another paper, it's called Building Sustainable Energy Systems, Homeostatic Control of Grid-Connected Microgrids as a means to reconcile power supply, energy demand response management. That was in Renewable and Sustainable Energy Reviews in 2014. Why do I mention this paper? Because this was very, very important, in terms of the subjects that we're discussing now, okay? And that was in 2014, all right? I mean, 10 years have gone by and things have changed. But everything that has happened gives credence, and reaffirms, restates what we are mentioning here, what we are advocating here. The key contributions in this paper are comparisons of reactive and predictive homeostasis and case studies of distributed generation system, something that's becoming more and more ubiquitous here in Chile today. They're coming everywhere. They're increasing distributed generation systems, not only in central part of Chile, in Santiago and the metropolitan area, but also in the south. In the south, they're also doing a lot of that. Summarize the competitive insight from case studies and highlight technologies that enable predictive homeostasis. For example, Internet of Things, sensors, AI. And key points are the homeostatic control for microgrids and addressing supply-demand mismatches. There's another paper called Homeostatic Control, Smart Metering, and Efficient Energy Supply and Consumption, which I will show you a bit later, that is also very important, very significant. It was also published on renewable and sustainable energy use. The main focus of this paper was smart metering's role, okay? In Chile, we have smart metering since, I believe, 2015, okay? That's when they were installed, okay? So every home now has smart metering. So the role of smart metering in enabling homeostatic control, okay? My hope is that we someday see homeostatic control systems in place, making use, of smart metering, improve resource allocation for hybrid microgeneration systems. I use ChatGPT. Doesn't make very good figures, and sometimes, but you can have an idea here. This is a representation made by ChatGPT, of energy homeostasis in power systems. Okay, and you have here conceptual flow chart showing energy homeostasis in power systems. The chart includes input box, renewable energy sources, solar, wind, whatever, an arrow leading to homeostatic control system. Number 3 is within homeostatic control system subcomponents labeled predictive control and reactive control, okay, which we already talked about. Energy demand balancing, which is a key aspect of energy homeostasis, energy demand balancing. Another, in number 4, another arrow leading from homeostatic control system to electric power distribution, the connection, residential, commercial, industrial, etc. Okay? So this is somehow a representation that now there's a book that I recommend also that you can read. It's called Spot Pricing of Electricity by Fred Schweb, Michael Karamanis, Richard Towers, and Roger Bond. This is the group that I was talking about from MIT. This was, I believe, one of the last publications that they made before the death, of Fred Schweb. Fred Schweb passed away, I believe, in 1989, that year, Fred Schweb, or 1990, somewhere around there. So this is the concepts are also discussed here. There's another good representation done by ChatGPT. You can see, batteries, smart meters, renewable energy, different customers, commercial, industrial, residential. Okay. So the concept of grid flexibility and energy balancing comes here. Okay. Very important. It highlights how renewable sources, smart meters, and energy storage interact with the central grid, the central power grid, and the end users, okay, the consumers. The key elements here are decentralized solar panels and wind turbines feeding energy into local substations. Second, flow lines depicting energy balancing using smart inverters and battery storage. I have a student doing a big project now. He's an undergraduate student doing his final project on smart inverters, okay, which is an important line of research today. And third, homeostatic adjustment mechanisms to show dynamic shifts in demand. So the external inputs, renewable energy sources, homeostatic control. This is based on the figure that you just saw. Homeostatic control box, subsystems for reactive control and predictive control. And the purpose of this is to demonstrate how energy flows in a distributed network with homeostatic control work. Okay, so you have decentralized solar panels and wind turbines feeding energy into local substations, which is something that will happen. I mean, it's happening in parts of the north of Chile today. Okay, where you have large wind turbines and also have solar plants in the northern Chile, far north, and that's happening today. Okay, flow lines depicting energy balancing using smart meters, inverters, and battery storage, and homeostatic adjustment mechanisms to show dynamic shifts in demand. Energy demand versus power supply versus power supply balancing chart. Predictive versus reactive. Reactive system demand and supply mismatch peaks are visible with corrections only and deviations. I'm sorry, corrections after deviation. Whereas predictive system supply anticipates demand curves using forecasts and corrections are smoother. Microgrid with smart meter feedback loops, purpose to show how smart meters help maintain homeostasis in energy systems by providing, information. House icon with solar panels and smart meters, flow arrows indicating real-time energy consumption, data sent to the grid operator, and feedback loop from the grid to the home, adjusting power inflow based on updated prediction. Okay, so that's essentially how a system works. Some equations. Well, here we present a simplified version of key control systems. Power net power output is power generation plus power in storage minus the power demand. Okay, the power generation is essentially renewable power. Okay, power generated by the photovoltaic plant, the microgrid. Okay, whatever the size. The power storage, power adjustment from storage from the storage unit. Battery bank. So reactive versus predictive homeostatic controller. Reactive feedback arrow after disturbance, predictive algorithm input with future forecasts around arrows showing adjustment in advance. Flowchart structure, renewable energy generation nodes, icon solar panels, wind turbines feeding energy into the microgrid. The description, power generation varies with weather conditions and time of day. Homeostatic control system, subsystem, predictive control, forecasting demand, supply, balance, and reactive control, real-time corrections. Action, when renewable generation exceeds demand, the system will adjust itself, charging batteries or shifting loads to lower cost periods. That is essentially what French Webb and his group advocated for. They advocated for that. That's what essentially they discussed. Back then, they didn't have the technology that we have today. So today, this is absolutely possible. Okay, and that's why I'm trying to convince the electrical utilities, Enel, which is the one I have a collaboration with, to get these going, and incorporate this. But I guess we'll have to wait for the distributed generation park, to increase more, that they, when that comes, they'll feel the need to incorporate homeostatic control. I believe they'll have no choice, because it makes sense, We already discussed about the energy storage unit and its importance. Smart meter feedback, also very important, and load management. Okay, load management is something where a lot can be done. Especially when you have residential, commercial, industrial settings. You can work that out. For example, a simple scenario: midday solar generation peaks. Okay. The system charges batteries and shifts industrial loads to minimize energy waste. When evening approaches, on the other hand, predictive control anticipates demand increase and preemptively adjusts power flows by discharging batteries. That scenario, which I'm trying to sell to the electrical utility, will come. Okay, that will come. And you need to have a system that can manage that well. Okay, and that's why I advocate for homeostatic control system, and to incorporate energy homeostaticity. Let me turn this off so I can. Give me just 1 second. Okay. The phone is interrupting all the time. Okay, so formula displaying homeostatic energy equation. Okay. Again, we already saw that equation. We know what these terms are. Power storage. Okay. Power adjustment via energy storage, positive when discharging, negative when charging. So power demand by users, power demanded by users. You have predictive control function, power adjust is equal to a function of power forecast and power actual. What is power forecast? Well, predicted power demand at time t. The system can predict that power forecast. Okay, we have the technology today to do that. Absolutely. And power adjustment is adjustment made to maintain balance at time t. The power actual is T minus delta T, which is essentially actual demand at previous time step. Okay. Now, in the case of reactive feedback formula, you have here Resiliency optimization process that balances predictive in real-time data. Now, in reactive case, in the reactive feedback mechanism case, you have power new equals power previous plus Ke, K sub E, times power error. Okay, let's analyze this equation. Ke is a feedback gain constant. Okay, power error is the difference between the predicted demand and the actual demand. Okay, and power new is a new power flow adjustment after feedback correction. Feedback correction enabled by reactive homeostasis. The formula displayed for homeostatic energy equation, net power balance equation, would be this one. Power net is equal power generation plus power storage minus power demand. The same equation we saw before. Okay. So power net is net power supplied to the grid at time t. Power generation, power generated from solar, wind, or whatever. In Chile, it's mainly solar, like I said before. Power storage, power from the storage system, battery banks. Positive during discharge and negative during charging. And power demand is power demanded by consumers at time t. Now, the key insight here is here. Formula represents, the formula I'll show you right now, represents the balance of energy flows where the difference between generation and demand is compensated by energy storage. That's why I said before, energy storage plays a big role, okay? It's a key role, right? Because it raises the energy content of the system, allows for disposable energy at times when the sunlight is non-existent, when there's no sunlight, and it allows you to be more independent of the grid because the grid is expensive. That's the problem. It's a backup system, it's infinite backup, but it's expensive. At least in Chile, electricity has come up in price very significantly. Today electricity is very expensive in Chile. It didn't used to be that way before. But after the pandemic, they unfreeze, they did away with the freeze of the electric tariffs, and the price went up. So no more freezing of tariffs, and all the costs that was withheld now came in place. So people are having a hard time, especially commercials. They're big way up in costs. So between generation, demand is compensated by energy storage to maintain homeostasis. So that's the key role here, and I've shown this in my papers, and I advocate for energy storage very much. Okay. At first, I didn't advocate for energy storage, and took the grid as the main backup. But that changed after the price of electricity went up, in Chile, and in our case, it's gone up, like I said, very, very significantly, very way up. So power adjustment, in case of predictive control adjustment equation, power adjustment time t is equal to alpha times power forecast minus power actual. What is this? You have power adjustment, which is power adjustment at time t to balance predicted and actual values. Okay. Power forecast is the predicted demand at time t. Power actual at t minus delta t is the actual demand measured at previous time step, t minus delta t. And the alpha is the predicted control gain, a constant that determines the sensitivity of the system. Why is this important? Because this in real life, in real terms, this happens, okay? There's a sensitivity of the system issue, okay? Systems sometimes cannot respond, because of certain conditions, okay? For example, variations in the frequency, okay, which happens a lot, okay? So you have these predicted control gain, okay? So that's where equation is. And the key insight here is the formula shows how predicted control anticipates demand shifts by adjusting power output in advance based on difference between forecast and previous measurements. In the case of reactive feedback correction equation, you have power new equals power current plus KE power error times power error. What is this? Okay, power new is a new adjustment power after applying feedback. Power current is current power level. Power error, again, is the error signal difference between expected demand and actual demand. And KE is the feedback gain constant, which controls how aggressively the system responds to errors. The equation highlights the role of feedback in reactive homeostatic systems, correcting deviations only after they occurred. See? in predictive homeostatic control case, you have power new equals power previous plus KE times power error. Okay. So purpose side-by-side comparison, how reactive and predictive homeostatic control operate in grid-connected energy systems. Okay. Reactive homeostatic control equation is here. Predictive homeostatic control is here. Okay. Here you have a diagram. Let me show it. Let me get this off. Diagram showing how reactive control lags behind demand shifts, while predictive control anticipates them, resulting in a smoother supply curve. The demand peaks in the morning and evening are highlighted, illustrated the difference in response. Here it is. The system here uses historical data and trends to predict future demand changes. Example, F of t could be a machine learning model that predicts future demand spikes. A timeline showing, I'm working on a paper on this right now, I'm developing the machine learning model. A timeline showing how reactive control lags behind demand shifts, and while predictive control anticipates them, keeping supply curve smoother. Reactive versus predictive control timeline at different times of day. Now, the evolution of the energy marketplace towards a decentralized system, which is coming, everything I've talked about today points to that, decentralized system, especially with the advent of this distributed generation growing and growing in Chile, for example, where electricity customers play a more active role in balancing supply and demand. That has to happen. That has to happen. We cannot have a system that was like in 100 years ago. We need to have decentralized systems where you have different energy producers. Okay, you have microgrids of different sizes working. Today, we do have in Chile, especially in Santiago area, we do have microgrids, but there will be more and more. This is growing, absolutely growing. So key points include customer independence. Customer, both residential and industrial, commercial, become more independent by generating their own energy. Okay, customers also contribute to the grid by selling excess energy back to the grid. Like I said before, there's a law that allows you to do that, and you can do it. So that way you become a prosumer. Okay, you are a consumer, but you can also produce and sell the excess energy, surplus energy to the grid. Communication. We have wonderful technology for communication today. Okay, and of course IoT, which is in several of the papers we've done with Sarat, with Professor Sahu, talk about that. Okay, so real-time communication between customers and electrical utilities becomes essential for dynamic pricing. Okay, which is something again that was heavily advocated by Fred Schweb and his group from MIT. That has to come. Back then, it wasn't much of an issue. They pregonated this, they advocated for this, they show this in their papers and in the book. But we're talking about, early 1980s, okay? Back then, things were not different, Today, almost 40 years later, okay, 30 something years later, things are different, okay? And so we're living in a different world, and climate change and weather disruptions are very, very much an issue today, especially, and with that comes cost. Smart meters and connected devices enable this communication by continuously transmitting data on energy generation, storage levels, and consumption. Decentralization of power distribution. Traditional top-down control of power distribution is replaced now by decentralized network where distributed generation plays a significant role. Market coordination. Despite decentralization, a market coordinator, and every country has one. Chile also has a market coordinator, okay? Ensures that energy dispatch remains balanced, similar to how control centers operate today. The role is critical to avoid overloading the grid and to maintain energy reliability as decentralized systems increase. So you have decentralized energy nodes, you have smart communication layer, excuse me, you have market coordinator, central node, and you have key labels. Flexibility, distributed generation, a smart grid, which is a big issue today. Enel is working heavily on smart grid, and it's also incorporating large energy storages to the power distribution grid. They're working on that, and it's not the only electrical utility incorporating large energy storage, because they have to keep power going. You know, they cannot afford to have extended blackouts. And demand response, which is something we already talked. Again, another representation image generated by ChatGPT. Like I said before, they're not very good. But it somewhat helps illustrate, you know, the concepts. The need to incorporate homeostasis-based control systems in the design of sustainable energy systems. There you have the energy marketplace. So here is a conceptual diagram that we have illustrating decentralized energy marketplace, the way we can envision this, highlighting prosumers, smart communication, and the market coordinator's role incorporating reference. See, this is in our papers, okay? This is in several of our papers. This was in 2021. Okay, paper highlights the role of IoT-based intelligent system for demand-side management and renewable energy generation. I'll show you the paper a bit later. So IoT, now we talk about the technologies, okay, a little bit, okay. These are all technologies that you know, that you're well aware of, and that are today part of modern electrical engineering and power systems engineering. IoT-based monitoring and renewable energy. IoT devices such as smart sensors and data loggers, for example, send a real-time meteorological and operational data. For example, in case of Chile, you know, solar irradiance, very important, you know, temperature, rated power, solar panels, etc., you know, to cloud storage, right? The data helps them in predicting the current state of each solar panel and its efficiency, enabling photovoltaic power generation optimization. Big data, analytics, and decision-making. Collected data from multiple prosumers is aggregated and processed in the cloud, okay? Algorithms sift through the vast data to identify trends, create forecasts, and generate additional actionable insights, okay? This is very important also for predicting homeostasis. The system improves productivity by using only relevant information rather than the entire data set. Demand-side management, very important issue here. Demand-side management and energy balancing. Demand-side management, as you all know, are strategies used that can use IoT platforms, for example, ThinkSpeak, and Arduino-based implementations to adjust consumer energy use in response to local conditions. in response to load conditions. The goal is to optimize energy usage patterns to match renewable power availability, very important, supporting grid stability during peak or low generation periods. Implications for energy trading. That in case we were to have energy tradings, we don't have that inside yet in Chile, but maybe one day, that was also advocated by Fred Schweb and his group, energy trading. By integrating IoT-enabled data from photovoltaic systems and energy consumption data, the system can facilitate energy trading, making real-time energy transactions feasible. Now, today, what you can do is you have surplus energy generated by a microgrid. You can sell that to the grid, and the grid is obliged. They're obligated to buy this, at a regulated tariff, a regulated rate, and that's okay. Okay. Expanded prosumer section, include smart IoT sensors connected to solar photovoltaic batteries and smart appliances. That one day we'll get to that. I'm hoping that I'll see that day, that continuously monitored energy production and usage. Arrows from IoT devices to a cloud data hub to symbolize cloud-based monitoring and big data storage. New layer for big data analysis and IoT control platform, and a layer representing cloud-based data analysis labeled IoT-driven energy management. Okay, I think IoT-driven energy management will become a big thing, from the onward. I see it more and more, and that technology is growing in Chile and elsewhere as well, especially in the region. The layer processing large data sets to predict energy production, detect anomalies, and optimize load balancing. Demand-side energy management, or demand-side management, and real-time control. Add a feedback mechanism from a cloud to residential and commercial prosumers, showing demand response adjustment. And again, with the market coordinator role, which we already talked about. Another representation based on what I just read, this was done by ChatGPT. You can see here, cloud-based data hub represents a cloud storage for meteorological and photovoltaic performance data. Big data analytics node illustrates data processing and decision-making based on real-time solar power generation. IoT-based data demand-side management feedback, arrows showing the feedback loop from the cloud to smart meters, and Arduino-based control systems for real-time adjustment. And lastly, energy trading platform represents real-time transactions enabled by predictive insight from big data. I don't foresee energy trading platform at least in the near future in Chile, but in other places that may well be so. Concluding the presentation, let's talk about, well, before that, this is one of my quotes, the sustainability for me is essentially a systemic property, an operational one in nature rather than explained by exogenous factors. So it's something you engineer in the system, sustainability, okay? Not something that can be explained by external or exogenous factors. So that I really believe in. There's no need, to incorporate homeostasis-based control systems in the design of, there's a need to incorporate homeostasis-based control systems in the design of sustainable energy system. That's the name of a paper, I believe. So key concepts here. Sustainable energy systems face dynamic changes in energy demand and generation. That's for sure, okay? Especially with the integration of renewables, and that we're seeing today. We're facing this, and electrical utilities are facing this in Chile today. Therefore, homeostasis-based control systems are designed to maintain equilibrium by adapting internal and external changes. That's why there's a need to incorporate homeostasis-based control systems in the design of sustainable energy systems. That's my prerogative right there. Okay, these systems use predictive homeostasis, which anticipate future fluctuations, for example, solar generation patterns, peak demand, and adjustments, based on other factors in the demand, and adjust energy flows preemptively. Now, reactive homeostasis responds to immediate disturbances, reacts, for example, sudden demand spikes or power failures. There's a reaction from the system. Advantages. What are the advantages of homeostasis-based control system? Well, increased resilience, for one thing, increased resilience against renewable energy variability, for example. That's why energy storage is also important. Improved exergy efficiency, okay, exergy constant, by maximizing useful energy, thus increasing exergy levels. Reduce dependence on the main grid because of the cost, okay? And that's where another concept that I developed is called grid frac, which we'll see in a second, okay? Grid frac values. I developed two concepts, homeostatic index and grid frac. They're in 3 of my papers, I believe. Design considerations, sensors and IoT-based systems to provide real-time situational awareness. But we have technology, we can do that today. Machine learning models to refine predictive homeostasis algorithms, something we also have the technology for that. Adaptive response mechanisms for optimal real-time corrections, reactive control. So again, recapping, reactive homeostasis reacts to imbalance after they occur. You have key example here during the grid fault, for example, homeostatic control redistributes stored energy to maintain service, which is what is expected, whenever there's a fault. And I already mentioned to you what happened last year, where we had a big weather event and we had extended many days of blackouts in several parts of Santiago. So this is a big issue today with electrical utilities. So delta P, power correction, is KR times E of T, where this is the corrective power adjustment, delta P corrective power adjustment. KR, or K sub R, is the feedback gain constant, and E sub T is the deviation between expected and actual energy levels. I repeat, KR is the feedback gain constant, and E sub T is the deviation between expected and actual energy levels. Predictive homeostasis is power adjusted equals power forecasted plus power plus a function of predictive, okay? Where F predictive adjusts energy dispatch based on forecast trends. Combined operation. Hybrid homeostasis systems combine reactive homeostasis and predictive homeostasis to optimize performance under varying conditions. They enable utilities to efficiently dispatch energy within microgrids, improving reliability and cost effectiveness, okay, which are the main concerns today. Energy homeostasis is present in all living organisms, like we know, we've discussed already. So the interpretation here is a homeostatic control in sustainable energy system mirrors biological systems that maintain internal stability. Example, like a thermostat regulating temperature. Homeostatic energy systems regulate energy inflows and outflows to maintain optimal conditions. As a corollary, you have energy homeostasis applies to human environments, impacting power supply and consumption patterns. Something very true. Okay. So again, the key components we already know about, sensing layer, processing layer, and control layer. Sensing layer, smart meters, sensors for photovoltaic performance, and weather monitors. Okay, weather monitoring is very important, especially when places where you have changing weather patterns. Processing layer, data analytics for reactive and predictive control, predictive homeostatic control. A control layer, adjustments to energy flows based on demand response programs and real-time grid feedback. Okay. And that is also explained in this paper, Building Sustainability in Energy Systems, the role of thriftiness and energy efficiency in the drive of higher systems efficiency and exergy level. A paper that I'm working on right now. Okay. Now, before we finish, let me show you some mathematical things I'm working on right now. Homeostatic control systems can regulate power supply and consumption efficiently, creating incentives for thrifty and efficient use of electrical energy. Now, what is the thing here? The equilibrium, okay? And how do we achieve equilibrium? Well, the mathematical model shows this equation. Let's analyze this equation. UT is a predictive homeostasis variable, okay? This equilibrium is a function of all these predictive homeostasis variable, U of T, V of T, reactive homeostasis variable, and delta T, which is situational awareness and criticality factor. Situational awareness and criticality factor is very important, okay? And I will talk about that in my next paper. I'm working on that and developing the theoretical concept for that. But it's very important today, based on technology that we have, we can really use this situational awareness and criticality factor in energy systems. The interpretation of this is that equilibrium function balances internal and external stimuli, akin to a metabolic regulation in living organisms. That's the whole thing, akin to a metabolic regulation in living organisms. That's the key issue. How you maintain equilibrium, balancing internal and external stimuli. And this criticality and situational awareness factor comes from both, it's based on both external stimuli and internal stimuli, internal and external factors. This is the homeostatic index. This is in several papers. I'll show you in a second. Okay, that I developed. Homeostatic index measures the proportion of energy drawn from the sustainable sources, for example, from the microgrid, compared to total consumption. Power renewable divided by total power. Okay, renewable plus power from the grid. Why is this important? Because the higher the renewable power in the system, meaning the power that is being generated by the microgrid, and the power that is stored, that is in storage, the higher the energy content, the exergy content, and the higher the homeostatic index. Okay, so a value close to 1 indicates minimal reliance on non-renewable sources, meaning the grid. Okay, so you want to rely the less possible on the grid. Okay, why? Because of the cost. In our case, because of the cost. Okay, but also because the grid can come down, it can go dark, as it has happened several times before. I already explained that because of the weather events we have had, and also quakes sometimes. The interpretation of these encourages prosumers to maximize local renewable generation. Okay, I repeat that, encourages prosumers to maximize local renewable generation. The other function I developed is grid frac, which is also in my papers, represent a fraction of energy consumption supplied by the grid. Why is this important? You already know by now, I already discussed the importance of the grid and also the less, hopefully less reliance on the grid, because of the issues I already mentioned. We discussed about the cost and also the safety, the availability of the grid sometimes. So the equation is below here. You have a lower value indicates better independence, better level of independence from the grid. Okay. Grid frac is power grid divided by power total. Definition: exergy refers to the to usable portion of energy, like we said before. So sustainable energy systems must strive. This is my prerogative. This is what I advocate. Sustainable energy systems must strive for minimal exergy losses by optimizing renewable integration and balancing consumption. That raises the exergy level. And the key insight here is that when the system reaches equilibrium, exergy approaches zero. Okay, as you know. So I'll show you now the homeostatic index over time. I have a graph and a grid frac over time. Okay, we have both graphs here side by side. And the homeostatic energy management framework inputs solar generation, battery storage, and demand data. Outputs corrective and predictive actions based on reactive and predictive homeostasis. Feedback loop showing reactive and predictive adjustments. So here you have. You can see here. That's the homeostatic index. It's a peak at 12. And the grid frac, of course, when you have the best sun irradiance, solar irradiance, and the maximum production of electrical energy from the photovoltaic system, you rely the minimum on the grid. It's the minimum amount you need from the grid. Just to finish up some of the supporting literature you have here, and some papers that I'm sure some of you are aware. This is renewable and sustainable energy reviews. Review of grid tie microgeneration systems without energy storage towards a new approach to sustainable hybrid energy systems linked to energy efficiency. That was in 2014, I believe, or 2013. 2014, I think, at the end. The other one is homeostatic control, smart metering, and efficient energy supply and consumption criteria. There we tested several criteria. That was a very good paper, very celebrated. And means to building more sustainable hybrid microgeneration systems. These are another papers. Building sustainable energy systems, homeostatic control of grid-connected microgrids as a means to reconcile power supply and energy demand response management. That's a good paper. And another here, also renewable sustainable energy reviews, reviewing homeostasis of sustainable energy systems, how reactive and predictive homeostasis can enable electric utilities to operate distributed generation, which is something I hope to see, that they operate distributed generation system as part of their power supply services. I think that's coming. That's coming. And I've talked to them about it. So I'm very hopeful that in the next few years, we'll see that. And the last two papers, engineering sustainable energy systems, how reactive and predictive homeostatic control can prepare electric power systems for environmental challenges. That's in Procedure Computer Science. And this one, demand response for renewable generation in IoT-based intelligent smart energy management systems. And lastly, finally, one of 4 chapters I wrote for this book. It's called Low Carbon Energy Technologies and Sustainable Energy Systems. This was back in 2021. Okay, I wrote 4 chapters. You guys picked the one that gave the name, the title of my talk. Integrating green energy into the grid, how to engineer energy homeostaticity, flexibility, and resilience in electrical power distribution systems, and why should electric utilities care? Well, you know by now why they should care. So that's my talk. Okay. Thank you very much. Thank you for your attention.
Thank you, Professor. Thank you very much for your time and nice presentation on this topic and a delightful presentation. So participants, you have any questions, you can ask or you can send through chat box. Professor, there is a question on the chat box. What are the challenges using DI in common areas? Distributed energy resources.
Is there a question?
Yes, yes. What are the challenges right now we are facing for distributed energy resources?
Let me see if you guys can write the question. If there's any question, please write it down on the chat so I can. This is Krishna Rao. Please tell me which renewable energy source is the best for optimal operation of microgrids. Well, in Chile, Krishna is photovoltaic. The solar irradiance in Chile is one of the best in the world. So we rely heavily on photovoltaic energy systems. We do have some very good wind, strong wind in way far south and in the north, way north. But basically the rest of Chile is solar. Okay. Thank you for the comment. Any other questions? Please feel free. I just write it down on the chat, and I will. What are the challenges of using DERT, the distributed energy resources, in common areas? Well, the challenges are basically the challenges for the grid, okay? Because whenever you have these DERT, these distributed energy resources, like we're having now, that causes disruptions in the frequency of the electrical energy service of the grid. Sometimes when you have these large, not when they're small, but when they're medium size or larger, they can sometimes interfere with the frequency of the grid, of the power supply grid, and that creates an issue. We're doing research now with Enel, working with them and with other colleagues from Universidad San Sebastián, which is a large university here in Santiago, in Chile, not only in Santiago, but in Concepcion also. And we're working on virtual power plants. I don't know if you heard virtual power plants. We're working on developing virtual power plants for Enel, especially to tackle this problem, of of frequency disruption caused by their distributed energy resources in areas where there's large presence of distributed generation systems. You know, these especially these medium-sized and larger photovoltaic farms. Okay. What happens if there's communication? Okay, let me read this one. What happens if there's a communication failure between IoT devices and energy provider? Well, communications links can be redundant. You know, you can have redundancy, and if you have a failure with IoT, you can have other means of communication. But today there's plenty of technology to have redundancy in communications terms. So means of communications are very extensive. You know, and we today, for example, you have enough power in what's it called, Wi-Fi's. You know, you have you have in Santiago, for example, you have very powerful networks of Wi-Fi. So you also have power, you have means of communication that way. Good evening. Give me a second. Which software is best suitable for microgrid simulation? There are several. You know, you can use Python, you can use MATLAB. I don't have any big choice for that. You know. Good evening, sir. Can we design virtual power plants in real-time application? Yes, of course. Yes, and we are working on that now with NL. Okay, NL is having issues with frequency disruptions. Okay, they're having quality problems in their service, in the power supply service to certain communities. Okay, sometimes they even have blackouts or browns. You know, when the voltage goes down. So we're working on developing a virtual power plant for that purpose. Okay. And I'll be working on a paper for that too. Good evening, sir. This is
Yeah, this
what
Professor.
are
I
the
think so. Our next session will start by 7:45, 8 like that. So let's wind up here and we'll start the next session.
Let me respond the last one. The major challenges encountered in microgrid integration with the grid is essentially what I already discussed. The problems, you know, that create sometimes with frequency disruptions, okay? That affects the grid. And so it's very, that's why the inverter thing is very important, you know, good inverter, you know, and also you need to have this monitoring very well in place, because sometimes because of the consumption, the energy consumption and the changes in demand can cause problems, you know, when you have these microgrids, these power plants, these photovoltaic plants working, you know, connected to grid. So there's a lot of research being done on that extensively. So I think that will be.
Yes, Professor. Yeah. Thank you very much again for your time.